Welcome to this course on the foundations of continuum mechanics. Today we'll be talking about finite deformations, particularly through the topics on stretch ratios and finite rotations. So let us get started. Today's lecture is going to be an exception in the sense that we are deviating from our infinitesimal deformation theory and going back to a general case of finite deformations. We will define the quantity called stretch ratio, and then we'll be using that in the context of finite deformations. Then we'll talk about finite rotations, which sometimes confuse us with infinitesimal rotations that we discussed in the last lecture. And towards the very end, we will show that under the approximation of small deformations, the finite quantities degenerate to infinitesimal quantities. So let's get started with this lecture. As the name suggests, we define the stretch ratio as a ratio of the element length in the deformed configuration to the element length in the undeformed configuration, and this is denoted by a capital lambda, and we also have a subscript n hat in this case, which is used to denote the direction of the d capital X element. So just to draw our usual deformation picture, we have the point P and point Q here, which results in this d capital X, and the image of these points are small p and small q, which results in this d small x vector. So in the stretch ratio, we have the magnitudes of these d small x and d capital X. So you can see that if the stretch ratio is 1, that means the element has not changed its length or has not stretched, and if it's less than 1 or more than 1, that means it has either gotten smaller or larger. And just to differentiate different positions of point capital Q around capital P, resulting in different d capital X vector elements, we use the n hat symbol to denote the stretch in that particular direction. So n hat is simply the ratio of d capital X vector upon its magnitude. So let's start using it. So d small x squared is basically the dot product of the dx vector with itself, and this can be written as FIA d capital XA times FIB d capital XB, which if I move around the terms, this becomes d capital XA times the AI term of F transpose times FIB times d capital XB. And if you recall, this F transpose F was called the Green's deformation tensor CAB, and we'll note today that this Green's deformation tensor is the tensor that is used to quantify different scalar measures in finite deformations. Now if I divide both sides by d capital X squared, so we get d small x by d capital X squared, and this becomes d capital XA upon d capital X times CAB times d capital XB upon d capital X. So this is nothing but the stretch ratio in the n hat direction squared as n hat dotted with the C tensor dotted with an n hat. I'll box this relation. So the knowledge of C will help us find out the stretch ratio squared. And in a very analogous fashion, I can show that 1 upon small lambda small n hat is given as small n hat dotted with a small c tensor dotted with a small n hat. Now this lambda small n hat is defined as d small x by d capital X, where n hat is given as d small x vector upon its magnitude. So this is when you work in the spatial coordinates, by looking at elements in the deformed configuration and figuring out what was happening to them in the undeformed configuration. So here C is our Cauchy deformation tensor as discussed previously. Of course, this lambda capital N hat need not necessarily be equal to small lambda small n hat unless we find out that the n hat element in the material configuration maps to the small n hat element in the deformed configuration. So in general, they are not the same. So for the discussion today, we'll stay with the Lagrangian descriptions, and similar ideas can be used for Eulerian descriptions as well. So if we take capital N hat equals the direction I1 hat, then our capital lambda n hat squared basically can be written as capital I1 hat squared, and that is I1 dotted with the C tensor dotted with an I1, and this is equal to C11, which, if you prefer to use the Lagrangian finite strain tensor E, becomes 1 plus twice E11, because twice Eij was defined as C minus identity. So what we see is that the diagonal terms of the C tensor, that is the Green's deformation tensor, they denote the square of the stretches in the coordinate directions in the material coordinates. Now let's talk about longitudinal strain. That's given as small e n hat, and that's defined as d small x minus d capital X upon d capital X, and from the definition of lambda, this is simply lambda n hat minus a 1, which can be written as square root of n dot c dot n minus a 1. So if I take my n hat equal to I1 hat in this case, the longitudinal strain E I1 hat becomes square root C11 minus a 1, which again, if you prefer to write using the Lagrangian finite strain tensor, this becomes 1 plus twice E11 square root minus a 1. So actually from this, I can write E11, that's the diagonal term of the Lagrangian finite strain tensor capital E, that is E, the longitudinal strain along I1 hat direction, plus half of small e squared. Now for small deformations, what we see is that E11 just is small e I1 hat, because e squared is much smaller than e. And this agrees with the fact that the longitudinal strain in the coordinate direction is equal to the diagonal term of the epsilon tensor. So for small deformations, capital E degenerates to epsilon. Just like always, now let's talk about the change in angles. So if I have d small xi1 dotted with a d small xi2, that's two vectors in the deformed configuration. They can be written as d small s1 magnitude, d small x2 magnitude times the cos of the angle between them. And then I can also write this as d capital XA1 times F transpose times F times d capital X to B. So this is a C. So from these two, what I find is that cos of theta is the ratio of these two quantities. And on the right hand side, if I divide by d capital X1 and d capital X2, this becomes an n hat dotted with a C tensor dot n hat divided by the stretch ratio lambda for, well, these are 1 and 2, for in 1 times lambda for the element along n2. Theta is the angle between these two vectors in the deformed configuration. So now if I choose my n1 hat vector as I1 and n2 hat as I2, this is what I get. Cos of theta 12 is C12 upon lambda I1 hat times lambda I2 hat. And if you remember, lambda I1 hat was square root of C11 and lambda I2 hat was square root of C22. So the knowledge of the Green's deformation tensor C tells us what is the angle between elements which were oriented along the coordinate directions in the material configuration. Now, if we choose to work in the principal axes of C, that is our 1, 2 and 3 directions are x1 star, x2 star and x3 star axes which coincide with the principal directions of the C tensor, then cos theta 12 is a 0 because C12 in the starred coordinate system now for C becomes a 0 because C becomes a diagonal tensor in its own principal coordinate system. So this implies that the principal axes, they stay perpendicular in the deformed configuration. So if this volume element, which is oriented along the principal directions of C, gets deformed, then it is only allowed to stretch but not shear. Of course, it can rotate as a whole, but we're not interested in that. So if I try to relate the volumes in the deformed to the undeformed configurations, first I'll have to find out d small x i's. So they are d capital X i's times a stretch in the corresponding direction, and the ratio of the volume in the deformed configuration for the small element to the volume in the undeformed configuration is simply the 3d small xi's multiplied together divided by the 3 capital Xi's, and this is nothing but the product of lambda I1 hat, lambda I2 hat and lambda I3 hat, which in terms of C can be written as C1, C2 and C3, which you can see is the third invariant of the Green's deformation tensor. So if I'm interested in knowing the volume change, all I have to do is I have to find the determinant of the C tensor, which actually is the third invariant of C. I don't have to transform it to the principal coordinates as such. Now we move on to the second topic of today's discussion, that is on finite rotations and stretch. So when I decompose a tensor, I either look for an additive decomposition or I look for a multiplicative decomposition. So an example of additive decomposition was that this displacement gradient tensor was written as a sum of its symmetric part and a skew symmetric part. So that is when we decompose the displacement gradient tensor additively into two other tensors which split the motion into a pure strain and a pure rotation. But this was possible for infinitesimal deformations. On the other hand, the multiplicative deformation, which is also called polar decomposition, it decomposes the deformation gradient tensor for example, into a rotation tensor and a symmetric stretch tensor. We can also do the other way. We can have a symmetric stretch tensor and a rotation tensor. So these R's, they are rotation tensors. So they basically are orthogonal. And this U and V, these are stretch tensors and they are symmetric. By the way, this U is called the right symmetric stretch and V is called the left symmetric stretch. And although we call it a stretch, it contains shear too. So additive decomposition worked for infinitesimal, but multiplicative decomposition, it works for finite cases as well. Let me explain this to you through a figure. So let us say we have an element like this and it deforms to an element like this. So for this deformation, we can go in two steps. In the first step, we simply stretch it. So this is applying a stretch to the deformation through the symmetric stretch tensor. And then we rotate it, which is applied through the rotation tensor R. On the other hand, we can first rotate it 90 degrees clockwise. So this is applied through a rotation tensor, and then we stretch it, which is applied through a symmetric stretch tensor. So if you have an element dx, it goes to d small x prime through, let's say we're taking the upper root through u, and then it goes to a d small x through a rotation. So I can write my d small x vector as u times d capital X, and then my d small x becomes r times d small x prime, which actually is r times u times d capital X. So this r times u is our overall F tensor, which is the deformation gradient tensor that helps us link the d small x with the d capital X. So given the availability of F as a starting point, because the deformation is known, we'll want to split this F into an R times U, where R mathematically is a rotation tensor and U mathematically is a symmetric tensor. Without showing the steps, I will write the decomposition here. So U is given as a square root of C. So this basically means in terms of matrices that U squared, that is U dot U, is equal to C. And the rotation tensor R then is simply F dotted with a U inverse. So let's write the procedure for solving a problem. So we have a deformation or a motion map given to us. So from that we can find F. From F we find C, that is F transpose F. And then we find the eigenvalues and eigenvectors of C. That gives us a C star. And through the eigenvectors of C, I get the transformation vector A, which takes us from a C to a C star. Now U is a square root of C. When working with diagonal matrices, it's very easy. So I can find U star, where the diagonal terms of U star are simply square roots of the diagonal terms of C star. Then I go back to a U through the A inverse transformation. because ultimately we have to write everything in our OX1, X2, X3 coordinate system that we started with. And from U I can calculate a U inverse, and from U inverse I can calculate an R. So we have the R now, and we also have the U now, and that is what was required for the polar decomposition of F. Now you may be wondering that if this is for the finite case, does it happen that under small deformations, this R becomes the omega ij tensor, and this U becomes something like an epsilon tensor? And the answer is yes. Let us see that. So Fia is defined as xi comma a, which actually is ui comma a plus a delta ia. So starting with the definition of u squared, which is c, which basically is f transpose f, so that's fia times fib. So let's call this ab components, and fia can now be written in terms of u and delta. So this becomes ui comma a plus delta ia. And remember, under small deformations, this square term can be neglected. So this simply becomes and remember this is u ab squared. And we are interested in u, so u is a square root of this. And if you recall that we used to write in polynomials that if we have 1 plus x to the power of n, that can be written as 1 plus nx for small x values. So in the matrix algebra, this also holds. So this becomes, this is like a 1, so delta AB plus, now n is a half here, half of UA comma B plus UB comma A. Now UA comma B minus delta is this. And this is nothing but your epsilon AB. That is the infinitesimal strain tensor. And this here is like our displacement gradient tensor, because displacement gradient was f minus I. So this is something like that. So what we notice is that the symmetric stretch tensor in finite deformations boils down to our strain tensor, which is also symmetric in the infinitesimal deformation assumption. So strain contains all the information of stretching and shearing, which was taken care by the U tensor in the finite deformations. Now let's talk about the rotation. So in a very similar fashion, R, which was defined as F times U inverse, will be written as, so the AC component of R becomes this is my F tensor, FIA to be specific in this case, and then we have a U inverse. Now again remember 1 plus x to the power of n is minus 1 here, so this can be written as 1 minus x. So this U inverse becomes delta AC minus a half of UA comma C plus UC comma A. So I'll expand this now. We get these terms, but again, this is a product. So for small displacement gradients, this can be neglected. And then we have a UI comma C and UI comma C here. So this simplifies to delta AC plus half of ui comma c minus u c comma I. Now this RAC minus delta IC. Remember, we want to work with displacement gradients, not the F tensor. So we have to subtract an I here. And this is a skew symmetric tensor, half of ui comma c minus u c comma I. So we have shown that under infinitesimal deformation assumption, our rotation tensor degenerates to a skew symmetric tensor, which was like an omega IC in our infinitesimal deformation theory. So hopefully today you were able to understand the idea of finite deformations and how to deal with that. So this will allow us to solve problems for finite deformation cases and to be able to quantify the motion in those finite deformations. So this brings us to the end of this lecture, and in the lectures to come in this week, we will now talk about situations where we have displacements having continuously. That is, we'll talk about the time rate change of displacement and the corresponding quantities for those cases where we have materials flowing continuously. So thank you very much, and I will see you in the next lecture.